We're going to pick up in this optional video by talking about the binomial distribution. I mentioned it briefly in our last spreadsheet, and for those of you who are interested, we're going to try to now link why this if function that we used down column C is actually a special case of the binomial distribution. So just to refresh your memory, we established a population size of individuals in cell C5. Let's just say that we're going to focus on 5 individuals. And we then assigned each individual a random number, and we entered an equation that said if the random number is less than the survival rate that is stored in cell C2, then we would have the spreadsheet return the number 1. Otherwise, we would have the spreadsheet return a 0, indicating that the animal has died. This is a particular case of the binomial distribution, so in this very short video, we're going to just very briefly introduce the binomial distribution. The binomial distribution requires 3 arguments. You need to enter the probability of success, the number of trials, and the number of successes. And oftentimes when people introduce the binomial distribution, they'll talk about it in terms of flipping coins. So for example, if I flip a coin 5 times and the probability of a heads is 0.5, then I want to know what is the probability that I will flip my coin 5 times and end up with 3 heads. The key thing here is that there are just 2 outcomes, and that's what the bi in binomial stands for, 2. So this is a situation where a heads is represented as a successful outcome and a tails represents a failed outcome. So this distribution is useful for presence absence, live or die, and that's the case that we're talking about here. So the first thing we need to do is decide whether our success is a death or a live individual. So if we say that the individual, we're really interested in the probability of surviving, then the probability of survival is represented here. So if we let that be 0.6 now, then we're interested in asking, out of 5 individuals, with a probability of survival of 0.6, what is the probability that we end up with 3 out of 5 survivors? And in Excel, we can use the binomial function to answer that question and to get the probability. Now, I encourage you to go to a reputable site and learn about the binomial distribution. Here, we're just going to introduce you to the function in Excel that will compute that for us. And this is called the binom_dist function. So if we type in binom_dist, binom.dist, we'll find the function and then open it up, and you'll see that it has 4 arguments. So the first argument is the number of observed successes. So the number of successes out of your particular trial. So here we're going to reference cell F5. The number of trials is the second argument, and we'll reference cell F4. The third argument is the probability of success. Here we will enter that in cell F3. And the last argument, we have to specify whether we want the cumulative binomial distribution or the probability mass function. We want the second one, so we'll enter false here. And I don't want to spend a lot of time going through this. What is a probability mass function or the cumulative distribution? We're aiming for a good intuition of what these are. And for now, though, you can see that Excel is returning a result, and this is telling us that the probability of observing 3 successes out of 5 trials, given the probability of success is 0.6, is 0.34. So that, in a nutshell, is the binomial probability function. So if I change the number of trials to 10, and I keep the probability of success the same, now you'll see that the spreadsheet will update that calculation using the binomial function for that. We can graph the binomial distribution, and we're going to use this portion of the spreadsheet to do that. So we're going to keep our number of trials to 5, and remember these represent 5 individuals in the population. And here we're going to ask, what is the binomial probability of observing 0 out of 5 survivors, given the probability of survival is 0.6? What is the probability of 1 survivor, given the probability is 0.6? And so on. So we're just going to use that same binom dist function, but this time, instead of referencing the number of successes here, we're going to reference the number of survivors down column H. So let's find the binom dist function once again. And here the first argument is the number of successes, or the number of survivors. So we'll enter H3. The number of trials will still be stored in cell F4, and we'll anchor that. The probability of success, or the probability of survivorship, will be stored in cell F3, and we'll anchor that. And here we again want the probability mass function. What is the exact probability? And if we copy this through, then we will see an example of the binomial distribution. So this is just a histogram showing these different outcomes. Now you'll notice that we've entered the binomial distribution with a title, and we've specified the number of trials as 5 and the probability of success, or the probability of survivorship, as 0.6. So this distribution looks at all of the possible outcomes that can happen when we have 5 individuals in the population. And if you add all of these values up, you should see that they must sum to 1. So let's prove that to ourselves, and you'll see that they do sum to 1. And that should make sense, right? If we have 5 individuals in the population, then and the probability of survivorship is 0.6, then there's some small probability that 0 out of 5 will survive, a little bit higher probability that 1 out of 5 will survive. There's a much higher probability that 3 out of 5 will survive, because this is the expected value. 33 is the same as 60% of 5. So the binomial distribution is controlled by these 2 parameters. It's the trials and the probability of success. And if we change any of those, or either of those, then we'll see that the shape of the distribution also changes. In this graph here, I've only shown up to 5 trials, and so we're going to keep our number of trials to 5 or fewer. Otherwise, we're going to end up with problems. For example, if I enter 10 here, then now we see that the area underneath these bars does not add to 1. That's because there's a chance that 6 or 7 or 8 or 9 or 10 individuals would also survive. So let's keep that back at 5. The other function argument that we can try is the cumulative binomial. And let me enter that and show you what that means. We'll again find the binom dist function, and the argument will be pretty much the same as we had before. We're going to ask, what is the probability of 0 survivors given the number of trials stored in cell F4? And we'll anchor that. The probability of success will be stored in cell F3, and we'll anchor that. And here now, let's enter the word true, indicating that we want the cumulative binomial distribution. And if we pull this down, you'll see that it's just accumulating across these different results. Here I have more decimals displayed than this case. Let me just make these match so it makes it more clear. So in the case of 0 survivors, the binomial mass probability, the exact probability, is the same as the cumulative. If we go to 1 survivor, though, the probability of getting exactly 1 survivor out of 5 trials is 0.26. But the cumulative function is telling us what is the probability of observing a 0 or a 1. So we're going to add those two numbers. 0.26 plus 0.08 is 0.34. So this is just accumulating down the column, and you can see that we end with the number 1 because as we add and consider more outcomes, we're considering all of the possible outcomes there are. Now, how does this relate to our if function that we used down in cell C17? Well, here we're dealing with a special case of the binomial distribution where the number of trials is 1. So let's enter the number 1 in cell F4. And of course, we're getting an error here now because we can't observe 3 successes out of 1 trial. So the number of successes must be 0 or 1. We can't have more observed successes than there are trials. And so now we're asking, what is the probability of observing 0 survivors when the probability of success is 0.4? And the answer is a 60% chance. Let's flip this around. What if the probability of success is 0.6, like we had here? Then we're asking, what is the probability of observing a 0, a failure or a mortality, when the probability of survivorship is 0.6? And the answer there is 0.4. So this is another way of saying that we expect that 40% of our outcomes will result in a death, and 60% of our outcomes will result in a survivorship. The other way to think about this is to stack these two. So anything random number between 0 and 0.4 will result in an outcome of 0, and any random number between 0.4 and 1, we'll just move this bar right over here on top, any of those random numbers will result in a number 1 as an outcome. And that's exactly what we have done with this if function. Our if function says, is the random number less than the value stored in cell C2? If it is, we'll return the number 1. Now let's just see how that looks over here. We're going to find this random number, 0.42, on this graph, right over here. 0.42 is up here, and so we would return the number 1. And that's exactly what we're doing with this if function. When you are dealing with a binomial distribution and you have just one trial, a trial is called a Bernoulli trial. And that's basically what we've used in our spreadsheet, whether we knew it or not. We've invoked a Bernoulli trial. So let's try it a different way here. We're going to enter a random number, and this time we're going to use the binom inverse function. We're going to find that function, binom.inv, and we're going to use this function to return a 1 or a 0. And this will do the same thing that our if function has done, except that we're going to be using the binomial distribution directly. So the number of trials is going to be 1. The probability of success will be stored in cell F3. And the alpha here is going to be the random number. And look at what this is saying. Returns the smallest value from the cumulative binomial distribution, from which the cumulative binomial distribution is greater than or equal to a criterion value. Our criterion value is the random number that we're giving it. So we'll reference cell F7 and then we'll press OK. So the same idea here. Let me just change this random number to match our first individual. And I'm going to press F9 until I get a result that makes some sense. But what you should see is that when random numbers are chosen, we're going to again find where they fall on this cumulative distribution and we'll return the number of survivors. So in this case it's a little bit backwards, but the result is the same. This time we're looking up this random number and we're finding where it falls in the cumulative array. So it's finding 0.448 and then it's returning the number. So 0.448 is associated in this column and it's returning this number 1 for the number of survivors. So in this case it's backwards than the if function. In our if function we said any random number less than 0.6 is equal to a survivorship, and anything between 0.6 and 1 will represent a mortality. Here we've just done a little bit of the opposite. We're saying any random number between 0 and 0.4 represents a mortality, and any random number between 0.4 and 1 represents a survivorship. So just a small little difference, but the end result is the same. So that is the binomial distribution. It's one of the most important distributions you can get familiar with in terms of modeling because we use it for all kinds of modeling problems. And in this particular example, we used it to model mortality or survivorship. But it comes into play for any kind of problem where there are only two outcomes.